Hi everyone, welcome to another episode of the Common Lisp Study Group. I'm your host, Ram Badam with Atlanta Functional Programming. Uh, Sorry, this is our first episode back from our short hiatus of a couple of weeks. And well, actually, it's been a month since we've had the Common Lisp Study Group. I hope all of you had a nice month of June. I was off during that time, but now I'm back. Last week, unfortunately, I was unable to um, actually do the stream due to being somewhat under the weather, so I apologize for that. This week, we're going to be finishing up just basically our discussion that we've been having the last few weeks on um, the low-level efficiency issues that was mentioned in Chapter 10 of the Common Lisp, well, the book, Paradigms of Artificial Intelligence Programming Case Studies in Common Lisp by Peter Norvig. Um, Today specifically, we're going to be covering choosing data structures. Uh, this is a pretty important topic for software engineering in general, but in terms of writing in Common Lisp in particular, it's particularly important, just mainly because of the fact that, contrary to popular belief, Common Lisp, although the name Lisp stands for Lisp processing, does not mean that Common Lisp has only lists. um, and yes, it is true that the majority of the sequence operations and the APIs provided for lists actually work uh, quite efficiently with lists. Sorry, with Lisp's linked lists or lists in general. There are other sequence classes that we've talked about that are available in the standard library alone, and you can also actually go and leverage lists to actually implement other data structures that are more suited for the particular problems that you're attempting to build. For example, the book covers the queues implementation that is in a very early Lisp called BBN Lisp, called tconc, that we'll be covering today, as well as, and this is implementing actually queues itself, but there are other ones that you are available. The author actually created kind of a slightly implemented um, improvement of the queues data structure that is inside BBN Lisp and address some of its limitations. But uh, the main disadvantage of those will be that well, we'll get into the actual implementations of tconc versus the suggestions that was made by Dr. Norvig itself in a bit. Before I begin, if you guys enjoy our Atlanta functional programming videos, please like and subscribe, hit the bell icon so that you can hear about up-to-date and more new videos that are going to be coming on, both in terms of Common Lisp, as well as other videos related to excuse me, different Common Lisp or functional programming related topics. Additionally, um, as many of you know, Atlanta Functional Programming is a group that promotes functional programming, has a complementary or in many cases a default paradigm for programming large-scale software systems. We normally meet nowadays online, although we are in need of a home. So for those of you who are in the Atlanta area and who do like our materials and our talks, please feel free to reach out to me. I am Bugram on um, functionalprogramming.slack, as well as I am Bugram on the Lisp Discord server for those of you who are on the Lisp Discord server. Please reach out to me and let me know if you have a particular place that we might be able to set up a permanent in-person home, and we'll, schedule some talks at your place. You can reach out to me or my co-organizer, Judd Taylor, who's um, also on um, Slack, but I'll have him mention to the folks out there his aliases and how he would be best contacted. The easiest thing to do for contacting both of us at the same time is through Meetup. And For those of you who are not on our meetup page, please feel free to join our meetup just so that you can hear up-to-date talks that are not particularly streamed, but will be available for you to see in person if you are in the Atlanta area. So, like I said, today's main focus is going to be to talk about data structures, which is the last piece of the puzzle in terms of this chapter and in low-level efficiencies in general. But I thought we'd quickly, just breeze through some of the stuff that we've talked about up until now, just mainly in terms of just quick uh, memory, just so that folks who have not yet who are just joining but haven't had a chance to watch previous episodes of our coverage of paradigms of artificial intelligence programming can actually go ahead and just, get the 5 minute spiel on what we talked about. Basically, chapter 9 and 10 both talked about the topic of low level issues. Chapter 9 focused on mainly techniques to speed up code that didn't necessarily involve low level issues, and this was mainly efficiency in general. And it started with essentially talking about instrumentation and memoization, and it also dealt with lazy evaluation, as well as writing essentially high-level compilers that will compile a declarative version of a particular piece of code into a much lower-level piece of code that would run more efficiently inside um, the uh, the Lisp compiler or Lisp implementation of your choice. Uh, we also talked about caching, and we talked about caching in terms of memoization, and we also talked about uh, delaying the competition or partial results, which is kind of like lazy evaluation if you're talking about the case of Haskell. Um, but also we've talked about um, the second. Um, the ability to actually use lazy evaluation to create um, this sort of data structure that allows us to create infinite data structures. Okay, so the common example that the one that we started with was the creation of the integers, infinite integers class by starting from a particular start point. Um, and it allows us to, obviously increment it every time we call it. Um, this I will not cover specifics in terms of how we implemented this. We've already covered a lot of this before, but I thought I'd at least mention that to those of you who are just joining us. Finally, we ended chapter 9 with uh, how to instrument your code so that you can get information regarding what to optimize and how to optimize. And we briefly touched indexing of data, which we ended with a basic idea of implementing an update to the simplification program that we did in uh, when we talked about the Maxima clone that we covered inside chapter 8. That alone covered very basic stuff related to both indexing and application of compilation too as well. This is something again that I would encourage most of you who have not read chapter 9 to go through, just because some of these high level techniques, all right, again, caching, compilation, delaying computation, indexing, could actually speed up your program to the point where you don't necessarily need to touch the topics inside chapter 10. But if you did need to, chapter 10 actually covered many things related to cons free programming, avoiding cons as much as possible in order to speed up computations, because as many of you know, each time you allocate stuff in cons, you are incurring an overhead of actually traversing that cons since it is a linked list data structure, and so that could potentially slow down both code generation at an assembly level, but also additionally when you are running it at runtime, you have that possibility of incurring a cache miss, uh, which forces you to actually perform an I/O operation. We also talked about using type declarations. This is something that I mentioned multiple times on this stream, that types are available inside Common Lisp. You do have the ability to declare them both using the uh, declare syntax inside the scope of a function. In the canonical example that most people show you is a typical, add function where you add two integers and you can actually declare them both to be fixed sums, and you can then use AB to actually go in and generate code here that if you disassemble, you end up seeing that it takes advantage of the fact that we specified uh, the fixed num to actually create a very efficient um, add versus when you do a no add, generic add. You'll see that there will be the overhead of actually trying to figure out what the types of operations you're dealing, types of arguments you're actually dealing with, and it incurs creating a um, sorry, an overhead of actually specifying that at the assembly level. So this way, it can prevent, not only incorrect computation for adding um, arguments that may or may not actually be available, but also, you see, this is the difference right here. Specifically, you can see if we actually go in and blow this up here, you can see that we're actually performing the add in this situation here versus um, uh, actually calling this generic function once we've actually moved the two arguments onto the stack. And this generic function here is a very expensive operation, mainly because of the fact that generic plus needs to actually go and look at the tag bits inside each of these particular Lisp objects to determine what to actually add and see if actually it is the case that they need to um, perform error handling or throw a condition back to the Lisp REPL. Right. Um, one thing I forgot to call out when we talked about this before with type declarations is Alex signed big num. In the SBCL and in most Lisps, we do our automatic integer promotion. So in the case of fixed nums, if it is the case that you will see two large fixed a big num, all right, because you added two fixed nums that ended up overflowing, then what Lisp does is it automatically allocates a larger integer type for you and assigns the result to that integer type and return it. That incurs obviously an overhead of a memory allocation because we are dealing with Lisp objects right in memory, but it does have the benefit of now you being able to just do generic operations, and the underlying compiler will take care of making sure it decides which storage level is best suited for the result of the computation. So there are advantages and disadvantages there, of course, because of the fact that if you know, for example, you won't go beyond a such particular range, it might be uh, very expensive to do this allocation, and it may not be necessary actually because you're wasting space. But the easiest implementation of doing it is um, being able to do the generic case first and then have the user go decide how to tweak the code in terms of either adding more restrictive types or so forth to ensure that the result is actually um, a, a fixed size, so you don't have to worry about the allocation actually occurring. We also talked about very briefly how you need to avoid generic functions, as we talked about with generic plus, and also dealing with complex argument lists. Like you do not want to actually have very large argument lists, and we talked about the differences between um, having no rest arguments versus having optional arguments and versus having key arguments. Again, I would encourage you to actually go back and watch those previous episodes before you um, have a chance to actually go through this one. Um, Regarding unnecessary consing, we've actually talked about different ways of actually dealing with using make array and fill pointers and actually using aref effectively. And we actually concluded with that last week when we were talking about, sorry, before our short hiatus, we talked about the ability of creating a pre-allocated buffer that you could then use to allocate particular Lisp objects and then return them. So, given all the techniques that we talked about up until now, one could ask then, what is the importance of talking about um, data structures and it's effectively implementing data types with the most efficient implementations? Well, as it turns out, especially when you're dealing with Lisps and different Lisps, um, each Lisp, especially if they're designed with their own Lisp virtual machine, which many are, um, they v- the implementation of particular data types might vary from implementation to implementation. And at the time that Common Lisp was standardized, there were also hardware that actually efficiently executed Lisps, and even there, certain data types were actually more efficiently implemented in some machines versus others. So we want to go through and quickly talk about, just the three case studies that Dr. Norvig brings up related to data structures. All right. Um, Before I begin, just very quickly, for those who are listening today, are there particular questions that you may want to ask related to the material before? Okay, so let's talk about the first case study that he brings up, which is variables. This one is might surprise to some folks. Why is he calling this, a data structure? But the main thing he was talking about is the variables that we created in terms of pattern matching that we in a few chapters back. Now, specifically the use of them when we were talking about the Simplify program, okay? And we talked about in chapter 9 when we were dealing with the Simplify program that you can compile expressions in Simplify and get rid of all the calls to checking to see if a particular argument is a variable or not. Mainly because in those cases, it might it's more efficient to actually know ahead of time a compile time that something's already a variable and account for it. But suppose we had a runtime use case where we need to still know whether or not a particular thing is a variable or a function call or whatever, right? Well, in that case, you could potentially implement um, a make variable constructor and give a previously new variable and just so you might have a function called essentially make variable like so, make variable. And this guy will basically take in as an argument just a symbol name. Okay, let's call it a name. Okay, and what this will return is a gen temp. Okay, that implements. Actually, you probably would. Do we need to actually go and add? I may be messing this up. Hold on a second. Oh, you don't even actually specify a name. You can actually gen temp. I forgot. Actually, generates its own thing. So we don't need to do this. We could just do this, do that, and then when we call it, we could do make variable, and then you see that it will automatically generate these variable names right for you. Now, what use would that be? Well, you could then use that to implement a function that just checks to see if you a implementation of variable that just checks to see variable p, the predicate, and we check to see and we check to see if it's first a symbol and then whether or not the first element of that symbol p var and EQL. I think we could just do equal. We may need to do value equality instead of EQL. Yeah, we need to do value equality, so we can't use EQL. EQL only uses for EQ is for pointer equality. EQL is for certain types of equality dealing with I think mainly integer types, and this is just a pure value equality equal sign. And what we're going to do is we're going to take the first element and check to see if the first element of the sequence is a question mark. Okay, that's all we're doing. So what's nice about this is index for a list of linked 0. Second, did I mess up some implementation detail? Right. We want not the variable itself. We want the symbol name of the variable. Symbol name var. There we go. So if we call variable p on this, we could see that this will return true. And if we call variable p on, say, test, you'll see that this is false. Okay. That's particularly useful just because now you are kind of restricting the infrastructure to just dealing with variables of a particular type of name. Okay, so you're not dealing with all different variation of naming variables, but one specific one that's created as part of the Lisp infrastructure. But then you could speed things up based on this implementation because this is still too generic. We can actually speed this up by essentially inlining. All right, we can actually inline these variables, and then additionally, we could potentially just leverage keywords instead because keywords have their own namespace, right? And if you use keywords, then you could then just simply check to see if a particular keyword is inside the keyword namespace. Okay, I will show you both of these. Like we'll basically make some, so we'll comment this guy out here just to see the difference. Okay, and what we'll do is we'll create our make variable again, but this time what we're going to do is we're going to do gen temp, we're going to label it x, And now in Common Lisp, you have this thing called the reader macro for generating. Um, the reader macro is for looking up. I believe. Let's double check here. Right, is to evaluate at read time um, the generation of this particular variable inside of the keyword package. So what this does is by grabbing this keyword and make variable, we at read time automatically generate a um, a new variable with x and some label, and we return whether or not. Um, uh, well, let me just show you what it does. It does this. So when we generate it, you can see that it generates a keyword with a new identifier. All right. And what this does is now we can just simply create a new variable p var. And what do we need to do? Well, we have this keyword p that just checks to see if it exists inside the keyword namespace. And oops, there we go. And let me just do one thing. Let's unintern variable p because that does not need to exist anymore. And when we do variable p of, let's say, 1, you'll see that this is nil, but if we do variable p of x3, oh, sorry, not variable p x3, you'll see that is true. Okay. Hell, actually, if you design here x1, you can see that just because we defined it has a keyword, it'll know that it's a keyword, but the keyword doesn't necessarily need to exist. We can add that if we wanted to be more stringent, but this is actually kind of not necessarily particularly useful when you're especially going to inline both of these, which brings me to my next thing. So once we have these defined, we can actually go ahead and inline them. And remember, inlining is part of a proclamation, a declare proclamation. And what this does is it allows you to inline the function names by typing in, has a list because it's taking in a list. In line, there we go, and then we do make variable and variable p. What does this do? Okay, I think it's important to know. Well, what inlining does, this inline declaration here is that whenever you see a call to make variable, it will automatically replace that make variable calls a site with the inline version when compiling. I don't believe when it comes to macro expansion that it's going to do that unless you do a full expansion. But I know for a fact that once you do a proclamation and you attach it to this, it's basically the metadata for saying that, hey, this variable needs to be inline is attached, and when a particular Lisp function is compiled, it will go ahead and generate a um, an inlined version of these two functions. This allows you now to, at runtime, if you need it, actually deal with temporary variables and check to see at runtime whether or not you're actually dealing with variables or not. All right. Um, Another way to deal with variables is also to have structures. I don't think I'm going to cover this one just because I think it's a pretty straightforward exercise for folks who have had a chance to go through this. But basically, it's a lookup table and an attachment to creating your own read macro for reading in particular variables, and then be able to print them out by creating a print function. Um, as I mentioned at the start of all of this, Lisp uh, lists are basically the one data structure that everybody almost uses. Has like second nature, like it'll automatically just fall on their hands. It'll implement something has a list, and then try to measure to see if it's actually good enough, and if not, they would then attempt to try using other data structures like hash tables or multi-dimensional arrays like make arrays or vectors and so forth. Um, Ideally, for sequence types, you want to use a vector, honestly, because it's probably going to be more efficient. It's not going to be it's probably, it definitely is going to be more efficient because it ends up computing into an offset calculation. Um, the one thing to be aware of, though, is you need to determine the use case as to what you're trying to do with vectors. So, for example, if you're dealing with growable sequences, obviously you want to use an adjustable vector. That means you're creating a make array. Remember in the make array syntax, right? You have in here the dimensions that you're doing, but additionally, look at all the keyword arguments. There's whether or not you're dealing initial elements or initial contents, but the main things to look at is adjustable and fill pointer. Adjustable basically says that it will determine whether the capacity, if the capacity is filled. Adjustable basically tells Lisp, hey, grow the vector so that we can actually add the additional with additional capacity so that we can actually add additional data to the vector. All right, and it'll do that for you out of the box. Other data structures give you that ability. Most data structures in most standard libraries and other languages also give you an effectively what is an adjustable vector in Common Lisp. Okay, now the one thing to be aware of is um, the fact that given these data structures, right, whether you're dealing with hash tables or lists or vectors, most standard common lists will have um, a decent performance metrics to follow, all right? And this is I'm trying not to be partial here because I have been using and I almost use more daily is SBCL, but there are other implementations that have a lot of other different features for different use cases, and you have to make sure that the data structures that that list provides is performant enough for your use cases. And if not, you can always go and implement your own. Either if in the case of SBCL, we could use their user-definable sequence protocols to actually go implement a full sequence type that's adjustable, or you can try and use other data structures that are already at your disposal, such as hash tables and so forth. But the goal should be that you first instrument the implementation, figure out what the bottlenecks are, and then address them accordingly. All right. Um, I'm not gonna cover too much here on that beyond that for this particular thing. But before I go on, are there um, are there questions available regarding any of our material? Hey, I see we have some of our regulars coming back. Hi everyone. I see Bailey. Shout out to Bailey. Definitely long time. Um, I will. I'm glad that you joined us today. Um, Feel free to add any questions or comments on our discussion. I'm just going to keep on browsing through here very quickly regarding these last two sections, these two other case studies. Um, this other one is particularly interesting just mainly because I didn't know um, the just how simple, um, just because you have such a universal data structure, how simple it is to implement, say, a queue. Normally, I would um, the big O of the queue. So the big O of the queue that we're going to be covering a is still going to be implementing queues in constant time. So it's constant, well, sorry, constant space, but the obviously n elements being added to a queue is still going to be linear. I mean, sorry, n elements of adding to a queue is going to be constant. Being able to uh, uh, DQ on it is going to be also constant too as well. At least the approach that they're doing, because the alternative approach that I'm going to show you. Typically, if you're going to implement queues has stacks, um, sorry, if you end up implementing queues using regular lists, because it's easier to implement and stack in a list, because last in first out is pretty simple with cons. Um, the queue piece, because of car and cutter, would require still to um, traverse the entire list every time you on queue something. Because recall how the queue, you're actually essentially adding at the end of the list, and then you're popping from the front of the list, right? So um, this means then obviously you're dealing with uh, a traversal every time you add a new item to the list. So adding n items to a queue using a regular common Lisp list is going to be quadratic um, in terms of runtime. Okay, and it's taking n space. The alternative implementation will make it linear for traversal and constant, because you're dealing with two pointers. Um, uh, but we'd have I want to show you the two implementations that address this. Um, so the first one is uh, tconk from BBN Lisp. BBN Lisp, for folks who aren't aware, BBN is actually now Raytheon BBN. Their Lisp was popular in the 80s. I don't know if it's open source or not, but I'm sure those who are BBN Lisp users will correct me by writing in the comments. But one interesting thing about BBN is their tconk implementation, which is their way of implementing a queue, is uh, it well, it looks like the following. Let me just show here. You have essentially um, a an item that you're playing, the queue that you're dealing with, and in order to deal with the end of the queue, it sets the cutter of the queue, and by checking to see first if it's null, then if it's null, we will set the car of the queue, the first of the queue, to being the item and nil. Okay, so that means if we're dealing with an empty queue, it'll end up being the first item that you're dealing with in the queue. Otherwise, what it does is it creates a new con cell, and it attaches uh, the rest of the cutter of the queue, which is the rest of all of the items there, with the new item. So this is essentially attaching to, think of this as being the cutter of the actual rest cell. It's going to add this new item. Okay, so the way this would look like if we're dealing with an empty list is let's first define def parameter, our test queue, let me first compile this guy. Okay. And actually, you know what? What am I doing? Let me go ahead and put this here. Oops, sorry, here. And let's go ahead and add tconc, and let's just decide to add nil and make our item here also the empty list. Okay. So if we actually look at, oh, sorry, I have to make this a cons nil nil. Let's see if I could do that. Cons nil nil. Okay, so let's see what test queue looks like. It's just going to be nil. So now, remember what is coulter of test queue now? Test queue coulter is going to be nil. All right. So what we'll do is we're going to call now tconc on this guy and add 1 to it. Okay. So now if we look at test queue, you'll see that we have 1 1, which is a little bit of a misnomer, but the reason for that is because we're not actually dealing. We actually constructed a new element. The car queue is set to um, the new element 1 to it, and so it falls under line 27's case. And so by adding it, we added car queue to it. And the 1 comes in. Let's see if I do one more. Let me add one more item here just to make it easier for me. Okay. You can see that the queue is the car of this. Okay. But the coulter actually keeps that's the queue contents, but the coulter keeps the last element that was inserted into the queue itself. Okay. Um, this is how they kind of implemented the two pointers. Um, it had a disadvantage because adding the first element to the queue is different than adding additional elements. As you can see by that if statement, we're adding the first of the queue to that. So they had to add an if statement to figure out which what are we doing? Are we appending to the end of the to list, or are we adding it for the first time? There's a way of actually implementing this that the book covered that I wanted to actually cover because I thought it was particularly interesting because it simplifies this a little bit more. The first thing we need to do is we need to implement we're going to make sure that this gets properly inlined. All right, so let's go here. And this inlining is going to be our interface. Okay, so we have the contents of the queue, our constructor of creating an empty queue, on queue and day queue, as most people know, has our basic operations. The front of the queue, this front of the queue, remember, is basically grabbing the contents of the front of the queue without actually dequeuing it. and checking to see if we have an empty queue and the queue non-concatenation, which is destructively modifying the queue itself. That last function is going to be used when we are dealing with um, uh, adding elements to the end of the queue. All right. And this is particularly specific if you want to add multiple elements to the queue itself. All right. So let's go in the order in which so the book has it in the order in which we they what's it of ease of implementation. So the first thing is obviously how do we define the queue contents? Well, the queue contents is nothing more than the coulter of the queue. All right. And the reason for that is because the fact that you're dealing with excuse me, um, the the entire queue contents of every item that's inside of the queue itself. Outside, excuse me, um, outside the actual initial value. Now let's talk about the uh, making an empty queue. All right. So making empty queue is much similar to what I was talking about before. This is nothing more than checking to see if um, we start with an empty cons where the car and coulter are both the same. All right. And what we do is we set um, the element of the car to being the empty cell. Okay. This should be obvious based on what I mentioned before. Yeah, let me just do that. Hold on. There we go. That's what I meant. So now we have this. We have this. I haven't inlined these just yet, but we will add it. The next thing is obviously we want to be able to implement our two operations on Q and DQ. These all both take a value, which is the queue itself, because remember think of these as member functions. We are not using def class here, okay? You could potentially create this as a def class and deal with the what you call it, the def method implementations of these, but I'm focusing on kind of how the algorithm is first implemented. All right, so we have our two operations here. So in the first case, the on queue, it takes the element car queue, okay, to be implementing the rest of car queue with the new item and then returning the queue. All right, so let's see how, and then DQ here also implements pop. Now, why are we using pop here? Well, the reason why we're using pop is if you recall in the book, he mentions that he changed the orders of the field so that the car of the con cell is going to be the last element. That means basically you're appending to the car. Okay, so by setting car the value, you're essentially appending to the end of the queue, right? That's what onQueues implemented has with this particular technique. All right. Um, the DQ then obviously is to remove an item from the front of the queue is you need to pop from the rest of the queue and then deal with the fallout of the emptiness of the coder once you get to that point. All right. So here, oh, and then let's go ahead and uh, deal with the other two, which is front and empty queue. Well, what is front and empty queue? Front and empty queue are basically going to be all dealing with the queue contents, right? Front being um, the first of the queue contents, and then the empty queue is going to be whether or not the queue contents themselves is null, all right? Because then we have an empty queue. The final thing that we want to implement is the enconc, which is like if you have multiple lists um, on here, uh, and you want to add all of the list items, all right, into the queue itself. How do you do that? Well, one way of doing it is taking the car of the queue, okay, and hold on one second. My apologies. Give me a second here. Got to correct this. S. Okay, and let's do this here. That. That. No. That. Okay. This. Oh. Um, done. Okay. So you can see here what we're doing is we're taking the current value of the queue and we're taking every item that's in the list and we're just attaching to it. And since this is already a common a linked list, this is the same as attaching to the rest of the car, right? Now, for those of you who are getting a little confused by car versus using rest and first, you could think of rest because rest is basic coder. You're doing Kadar, which there are technically the Kadar and Kadar and CDDDR and all this kind of stuff, but this is kind of giving you the essence of this algorithm, which is basically saying that you're attaching to the end of the list the elements of all this list. So here in this implementation, it's nothing more than a pointer assignment to add stuff to the end of the list, given a list and queue, is literally you're appending the list by assigning the 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 next value if you want to live with the head of the new list that you have, and then that does the same thing. Excuse me for a second. So the nice thing about this is once we actually go in first, do mcr, and everything gets loaded. What is missing here? This is second. Okay. Okay. Okay, that's fine. That's fine. Something here is missing. Let me just do something here. Oh, yeah. Okay. That's what I'm missing. Okay. So MCR, everything's loaded. We have our definitions. So we could start with first make queue. Okay. And what make queue does is it just creates this empty nil list, which is particularly interesting. All right. So now let's see what happens when we do on queue. Okay. On queue item 1 to the queue. Well, we get the same implementation that we had before. Okay. R2 and so forth. But this time, notice how we're appending the list is now at the end, but the appending is now in uh, the on queue. The last of the list is actually in the car. The coder is actually the actual queue itself. Okay, so now if we do queue contents of this guy here, queue contents, you can see that we get the actual queue itself. If we do, um, let me set F our test queue to being this, so that we have our queue. Okay, and let's do what's the front of it? Well, the front is going to be the front of the the uh, the car, which is our one, obviously, right? Um, let's see what happens when we dequeue here. Okay, let's do test queue vc22. Okay, so now let's go ahead and run the final thing, which is queue nconc, and let's apply to our test queue list 3, 4, 5, 6, and 7, and we'll see what happens here when we do this. You can see 2, 3, 4, 5, 6, and 7 gets added. And why is that? Because the fact that we've actually said that the car, the queue, is going to be um, the last of the elements that you get from performing the assignment. All right. So this is a pretty efficient implementation of queues using 2 pointers, but naturally, you know, in general, the fact that we're still using a list has its disadvantages. Although in queues, it makes it pretty nice to implement this. And again, you're dealing with from a standpoint of this, you're still dealing with the standard runtime complexity of using a queue. The only difference is the space is now essentially effectively you're just dealing with 2 pointers in memory. You're dealing with a single well, not necessarily single console because of the fact that you are dealing with um, a list of multiple kansas. It's just that now um, the removal is constant time, the addition is constant time, um, and so n additions is just going to take linear time. All right, so just keep that in mind. Finally, the last data structure they went through, which I'm not going to really bore you with, but I'm sure most of you are um, have done this before in the past. This is implementing uh, tables. So you have key value pairs, um, and then you use the keys to actually look up the particular values. So there are ways of doing implementations of running key value pairs. Uh, Everyone knows that Common Lisp has a hash table, but there are other ways of implementing key value pairs other than just hash tables. The simplest way in Common Lisp is the associative list, and I'm sure many of you have seen this. This is your ASOC um, function call in Common Lisp. So you just simply create something with A, B, C, and D with like this. And if you do, oh, sorry, I have to do, let me do this again. Let's say that you had this, and then you do ASOC, and then you check to see item A in the list. Ooh. Did I put ASOC item A list? Hold on, I may have messed this up for a second here. Let's see. A star. Well, let me do this. Star. Get the stuff back. Oh, star. Star. Okay, that's what I need. So if I do that, star. I do ASOC item A list. A. Let me just do this. Let me just add def param A list. That. Okay, so now A list is that. Okay, so ASOC A list. This is not okay. 4. And let's do test EQL. I think test dash EQ is probably what I need to do here. Or EQL. Let's see. Not of type list. Which is it? Code A. So it's not able to find. Well, it's not that it's not able to find. It's treating a list as being a list. I think it's because the fact that I did not make this an appropriate associative list. Let me do this. Cons A. So the way that the book has it, I thought there was a better way of doing this, but we could do it this way. So you have a key value pair, right? So what you could do is you could do cons A. Hold on. Let me just do this. Set F A list cons A, cons B, cons C nil. I think is what, no, that's A, B, C, but I have to do cons of a cons. That's what I need to do. That's right, cons of a cons. So this needs to be also cons. That's what I need. Now, this gives us the list of A, B. Then we need to attach this to cons D nil. So this guy has to be cons D. If we do that, A is unbound. Oh wait, my apologies. I have to put these all in quotes. A, that. Now we have it. Invalid number arguments 1. Set F. I think I'm missing a cons cell here somewhere. Um, No, 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 no. This is the wrong thing. One second. I'm mixing things up with the data structures here. Associative list. So what I have to do is I have to first create this as a dotted pair. So first I have to create acons key A, datum value B, C, A list. A list is unbound. Hold on. There we go. So first, let me empty out A list to being the empty list for now. And now let's do this. Okay. And now we do acons d nil A list. Okay. And if we look at A list now, we see that, what did I do? This here's a, oh, I have to set CPWR set up A list to being that. And then do this. Oh, if I do this, this is not going to add a new list to the old list. Construct a new association list by adding key pair data to the old list. Okay, so let's see this. Acons datum, key datum is nil to the A list, and then return the A list. So let's see this. So this is what happens, okay? So now what you want to do is if you do asoc A from A list, what you get is ABC. If you do asoc D from A list, you're going to get nil, okay? Or in this case, it's a set D because of the fact that D nil is going to be the single list D. There's also other things like pairwise, pair lists, and all this kind of stuff that's available to you in the standard library that we covered in the past. You could provide the set of keys and datas, and it'll do essentially a zip um, of this. I could just quickly show you this. So if you do pair list, okay, let's do E F, okay, and then make our list G and H, and we provide a list here, and CPWR setup a list. You'll see that, oh, sorry. Do that. We get two dotted pairs here where F is mapped to G, H, E is mapped to G, has the key and the value, and then D and so forth are mapped to what we had before. Okay, so that's what pair list does. Association lists are the easiest way of creating a list of key value pairs inside Common Lisp Apologies for me to make it look like it's more difficult than it did. It's mainly because of the fact I forgot my acons and pairless functions off the top of my head. Um, the other one we've already talked about, the hash table. The book covers tries, which are prefix trees. I'm sure most of you have seen tries. There isn't a whole lot in terms of the uh, the try um, implementation that is stuff that we haven't seen before. So I'm not going to really cover it in too much detail here. The one thing I want to bring up here that I found interesting is the fact that the way he handles um, tries that have been keys that have been removed from the try is by adding essentially markers inside of the try data structure to check to see that it's deleted. Um, I if people are interested, I could do a follow-up video on this. I'm just it's the main implementation though is very much the same, except it's implemented in a tail recursive manner than that most people have seen in most books on implementation tries. I may do a follow-up on this just mainly because there are different ways of implementing tries, and we can try out different techniques for it when we cover more data structures centric sort of part of our series. Um, so that's actually it for chapter 10. Again, like I mentioned before, this was very basically a review of all the techniques that we covered up till now. It's important though to keep in mind these techniques because in later chapters of this book, I've noticed, especially when we start talking about chapter 11 through 14, which is covering logic programming and prologue, um, there are going to be places where some of these efficient techniques might be put in place, and we just haven't covered it yet. So that's why I encourage most of you who are following along just to be aware that knowing that these even exist, these techniques even exist, puts you far ahead at trying to understand some of the stuff that we're going to be implementing later on. And when we do cover kind of other macro type projects that we could cover in our ongoing study of this great language, um, these techniques will obviously become part of our tool belt that we'll use more often than you may realize. So next week we're going to be covering chapter 11. This is on logic programming. I hope all you enjoyed today's episode. Once again, if you joined us late, please and you like our videos, please like and hit that bell icon before you leave. And I hope you enjoy and have a great Monday evening. Bye.